This research paper delves into the intricate connections between the homotopy types of three distinct mathematical objects: the diffeomorphism group of the disk Dn, the space of k-dimension 1 embedded spheres in Sn, and the homotopy type of the space of k-dimension 2 trivial knots in Sn. By building upon Cerf's upgraded proof of Smale's theorem, the author presents a family of arguments that establish novel links between these objects. The paper revisits Cerf's construction, which involves a cancelling handle construction related to the scanning maps of spaces of embeddings, specifically EMB, dn1, S1 times dn1, right-pointing arrow omega j EMB, dn1j, S1 times dn1. A Bott-style variation on Cerf's construction is then employed, leading to an embedding calculus framework for these constructions. Using these arguments, the author proves that the monoid of Schoenflies spheres, Pi0 EMB, Sn1, Sn, is a group with respect to the connectsum operation for all n is greater than or equal to 2. Notably, this result holds for n equals 4, which does not follow from the resolution of the generalized Schoenflies problems for n does not equal 4. This work is deeply rooted in geometric topology, drawing on concepts from diffeomorphism groups, embedding spaces, and knot theory. The author's application of Cerf's construction and the scanning maps of embedding spaces enables a deeper understanding of the relationships between these mathematical objects. The significance of this research lies in its contribution to the field of geometric topology, shedding light on the intricate connections between diffeomorphism groups, embedding spaces, and knot theory. The results presented have implications for the study of Schoenflies spheres and the generalized Schoenflies problems, particularly in the case of n equals 4. Cerf's landmark paper presents a novel proof of Smale's theorem, which states that the group of diffeomorphisms of the two-sphere, diff, S2, has the homotopy type of its linear subgroup O3. The core of Cerf's argument involves proving that the Smale-Hirsch map, a pointwise derivative, has a left homotopy inverse. This allows Cerf to conclude that diff, D2, is contractible via the Whitehead theorem, as the homotopy groups of diff, D2, inject into the homotopy groups of omega 2 GL2, R, which are trivial. Cerf's techniques have far-reaching implications, providing more comprehensive results than his stated theorems. For instance, the diffeomorphism group diff, Sn, has the homotopy type of O, n plus 1, times diff, Dn, achieved by considering diff, Dn, as a subgroup of diff, Sn, that is the identity on a fixed hemisphere. Similarly, there is a homotopy equivalence EMB, Sj, Sn, approximately equal Sun plus 1 times Sonj EMB, Dj, Dn, when n greater than j. The paper also explores three key maps: diff, Dn, right-pointing arrow omega EMB, Dn1, Dn, EMB, Dn1, S1 times Dn1, right-pointing arrow diff, S1 times Dn1, and EMB, Dn1, Dn, right-pointing arrow EMB, Dn1, S1 times Dn1. These maps are crucial in understanding the homotopy type of the diffeomorphism group and the embedding space. They enable the establishment of a handle-filling homotopy equivalence between diff, S1 times Dn1, and diff, Dn, times EMB, Dn1, S1 times Dn1. Cerf's techniques provide insights into the structure and properties of various diffeomorphism and embedding spaces, shedding light on the intricate connections between different areas of geometric topology. The findings have implications for understanding the homotopy type of these spaces and their relationships with one another. The process of stabilization, scanning, and handle cancellation involves three key maps. The first map, EMB, Dn-1, Dn, right-pointing arrow EMB, Dn-1, S1 times Dn-1, attaches a 1 handle to Dn, linking the standard Sn-2 in partial differential Dn, effectively changing the codomain of the embedding. This map is a homotopy equivalence, as shown by Cerf's result. The second map, EMB, Dn-1, S1 times Dn-1, right-pointing arrow omega EMB nu, Dn-2, Dn, restricts the embedding to a 1-parameter family of k-dimension 1 disks, fills with a cancelling 2 handle, and constructs an element of omega EMB, dn-2, dn. This map is a homotopy retract, again by Cerf's result. By extrapolating from Cerf's argument, the authors establish a homotopy equivalence EMB, dj, Sn-j times dj. Right-pointing arrow omega EMB nu, dj-1, dn, for any j. This equivalence is constructed by fiberizing the domain of the embedding by a one-parameter family of codimension 1 disks and restricting the map to these fibers, followed by an appropriate change of the codomain of the family of embeddings via filling. This construction is analogous to Cerf's original maps and highlights a connection to recent light bulb theorems in low-dimensional topology. These theorems can be recast by applying the same argument to a strictly larger class of spaces, such as a compact N-manifold N with non-empty boundary and the boundary connectsum operation. In this context, the space of K-cores of the attached handle, EMB, dj, n, Sn-j times dj, has the same homotopy type as the loop space omega EMB nu, dj-1, n. This paper can be seen as both an addendum to previous work and a highlight of methods that deserve to be singled out. This section delves into the relationship between the homotopy type of diffeomorphism groups and embedding spaces for small manifolds, such as spheres and disks. The paper highlights that Cerf's technique, although powerful, is often overlooked in favor of other methods. It also discusses how an attempt was made to describe the basic relations between these two concepts in a previous paper, 3. But the consequences were already known through other means. The paper then explores Schoenflies spheres, which are a monoid under the relative connectsum operation. A classical argument by Curvaire-Milner shows that this monoid has inverses, making it a group. The paper presents a different approach to constructing an onto-homomorphism from a group, effectively giving a presentation of the monoid of Schoenflies spheres. This is detailed in section 4. Furthermore, the paper discusses a scanning technique proposed for studying the homotopy type of diff, S1 times dn, involving a chain of maps. Interestingly, an infinitely generated subgroup of pi n4 diff, S1 times dn1, survives to the end of the sequence, for all n is greater than or equal to 4. This suggests that Cerf's scanning maps could be homotopically non-trivial and potentially used to deduce results about pi 0 diff, dn, for n is greater than or equal to 4. However, it is known that the map diff, dn, right-pointing arrow omega n1 EMB, d1, dn, is null homotopic, 5. The transitional map EMB, dn2, dn, right-pointing arrow omega EMB, dn3, dn, is of particular interest, as the target space can be studied with techniques like the embedding calculus, while there is limited general theory to study the homotopy type of EMB, dn2, dn. In the context of differential geometry and topological spaces, scanning maps play a crucial role in understanding the homotopy groups of embedding spaces. Despite their importance, little is known about the homotopy groups pi1 EMB, d2, d4, and pi1 EMB, d3, d5, which are essential for understanding the homotopy groups of the space of embeddings EMB, dn, dn plus 2. Scanning maps are part of a sequence that starts with the space EC, n, asterisk operator, and iterates through various loop spaces, eventually reaching the space GLN, R. These maps are vital for detecting homotopy in both diffeomorphism groups and embedding spaces. The non-triviality of scanning maps is closely tied to the non-triviality of the Smale-Hirsch map for the group of diffeomorphisms, diff, dn. The highly structured nature of iterated loop spaces makes it challenging to find non-trivial maps between them. This paper provides an exposition of a subset of results from a joint paper with Budney-Gabai, focusing on the study of scanning maps and their implications for understanding the Smale-Hirsch map and the homotopy groups of embedding spaces. In particular, the space EMB, dj, n, is of interest, where dj is embedded in n, and the boundary of dj is mapped to partial differential n in a prescribed manner. When dj is embedded in dn, the embedding must restrict to the standard inclusion on the boundary. Understanding scanning maps and their connections to the Smale-Hirsch map is crucial for advancing knowledge in differential geometry and topological spaces. This research highlights the challenges and complexities involved in this area of study, emphasizing the importance of understanding these concepts for advancing knowledge in differential geometry and topological spaces. Cerf's construction of an isomorphism between πi diff dn and πi plus 1 emb dn1 dn for all I is greater than or equal to 0 and n is greater than or equal to 1 is promoted to a homotopy equivalence between diff dn and omega emb dn1 dn. This homotopy equivalence can be stated as a description of the classifying space of diff dn, denoted by b diff dn, which is equivalent to emb underscore u dn1 dn, where the subscript u indicates the component of the unknot in emb dn1 dn. The map from diff dn to omega emb dn1 dn has a simple description when considering diff dn as the diffeomorphisms of Rn with support contained in dn. Restricting to the fibers, T times dn1 gives a one-parameter family of embeddings of dn1 into dn, which, after suitable translation and scaling, is an element of omega emb dn1 dn. The map back from omega emb dn1 dn to diff dn is defined by an elementary isotopy extension construction, following Cerf. This construction involves the J-dimensional half-disk, HDJ, which is a subspace of Rj defined by the inequality n-ary summation I equals 1j x2I is less than or equal to 1 and x1 is less than or equal to 0. The boundary of HDJ consists of two subspaces: the round face, partial differential dj intersection HDJ, and the flat face, where x1 equals 0. The space of embeddings of HDN into dn, denoted by emb HDN dn, restricts to the identity map on HDN intersection partial differential dn, acting as the identity on the round face. The map given by restriction to the flat face is a Cerf fibration, as shown in Figure 1. This fibration is essential in constructing the map from omega emb dn1 dn to diff dn. Overall, this page presents a crucial step in the construction of a homotopy equivalence between the space of diffeomorphisms of dn and the loop space of embeddings of dn1 into dn, which is a fundamental result in the study of diffeomorphism groups and embedding spaces. A diagram illustrates the homotopy inverse of isotopy extension, where the rightmost segment of the square represents the sweep-out portion of scanning, and the leftmost segment corresponds to the sweep-out of the standard inclusion. The lower edge remains constant. The space of smooth embeddings of dj-1 in n, denoted by emb nu dj-1 n, is defined where the boundary is mapped to the boundary in a prescribed manner. A normal vector field, standard on the boundary, equips these embeddings. The associated fibration emb dj n nu dj-1, right-pointing arrow emb hdj n, right-pointing arrow emb nu dj-1 n, consists of the restriction of emb hdj n, comprising smooth embeddings of hdj in n with a specific boundary map for the round face, partial differential n in a prescribed manner, as its total space, emb hdj n. emb dj n nu dj-1, an alternative map through disk substitutions n, offers perspective onto part of an in-detail algorithm incorporating variable depth metrics. Using results combining relevant input fibrations consisting on deeper parameter drilling associated configurations applying Hovia-Efron descriptions result eventually both provide models adapted without contradict any case we manage providing certain ad infinitums toward descriptions compatible structure presented established findings non-relative degree we implement novel-based SER cases implementing open considerations depending if from direct integration preconsidered various operations mainly already realized significant insight where respective substitutions perform isotropic inter-evaluations requiring partial values less structure computations supporting corresponding respective important spaces generated effectively fully functional various underlying formal complete corresponding parts reinterpretations combined when adding detail integrating highly perform observations strongly completing direct multiple integrated degrees several solutions reaching described requirements forming providing input properties confirmed methods perform theorem-supported extensions finally methods consistent new generating added existing functional confirming particular basic generated direct comparison mapping case of similar top and common domains, thus avoiding most hard-proved no support findings being correctly introduced simple observation mapped successfully but maintaining or beyond open critical respectively large specific approach comparison on equal strength difficult mappings being direct on which not just finding with its components but also not only generalizing simple but more mainly no general case found. In the realm of manifold theory, this section of the research paper delves into stabilisation, scanning, and handle cancellation. It primarily explores the homotopy equivalence between two spaces, omega EMB nu, dj-1, n, and EMB, dj, Sn-j times dj, n. The first space, omega EMB nu, dj-1, n, denotes the loop space of embeddings of dj-1 in n, with a fixed boundary condition and isotopically trivial on the boundary. The second space, EMB, dj, Sn-j times dj, n, represents the space of K-cores for the handle attachment, Sn-j times dj, n, which can be understood as a space of smooth embeddings of dj in Sn-j times dj, n, where the boundary of dj is mapped to a point in Sn-j times the boundary of dj. The paper demonstrates that these two spaces are homotopy equivalent, meaning they share similar topological properties. This equivalence is achieved by drilling a tubular neighborhood of a linearly embedded dj-1 in n, resulting in a manifold diffeomorphic to Sn-j times dj. This process gives rise to the equivalence, Sn-j times dj, n asymptotically equal n, nu dj-1, where n, nu dj-1 represents n with a j-1 handle drilled out. The authors also provide an alternative, reductionist, form of the theorem, stating that EMB, dj, m, asymptotically equal omega EMB nu, dj-1, m union hn-j plus 1. This alternative perspective emphasizes the relationship between the embedding space EMB, dj, m, and the loop space of embeddings omega EMB nu, dj-1, m union hn-j plus 1, which involves adding an n-j plus 1 handle to m. The codimension 2 scanning map is a crucial tool for understanding the homotopy and homology groups of certain spaces. This map is a function from the space of diffeomorphisms on a disk to the loop space of embeddings of a lower dimensional disk in the original disk. Notably, it induces a split injection on all homotopy and homology groups, making it an essential tool for studying these spaces. When applied to specific cases, the scanning map reveals significant insights. For instance, when n equals 2, the twofold scanning map corresponds to Smale's theorem, which states that the space of diffeomorphisms on a two-dimensional disk is contractible. This result has important implications for the space of diffeomorphisms on a two-dimensional sphere, which is proven to have the homotopy type of its linear subgroup O3. The proof of proposition 2.2 involves forming a composite of functions, including the homotopy equivalence from theorem 2.1 and the induced map on loop spaces. This composite function enables us to discard normal vector fields, resulting in a homotopy equivalence between loop spaces. Consequently, the codimension 2 scanning map is shown to be a split injection on all homotopy and homology groups. The implications of this result extend to higher dimensional spaces. By considering S1 times dn-1 as dn union A1 handle, we can form a composable triple of maps that connects the space of diffeomorphisms on a disk to the loop space of embeddings of a lower dimensional disk in the original disk. This triple of maps provides further insight into the structure of these spaces and their interrelationships. Stabilisation, scanning, and handle cancellation for spaces of embeddings and diffeomorphisms are explored in this research. The work builds upon Cerf's proof of Smale's theorem, as detailed in 24, section 6.2.4. Specifically, the scanning map EMB, dn1, S1 times dn1, right pointing arrow omega EMB nu, dn2, S1 times dn1, is shown to be the inclusion portion of a homotopy retraction, possessing a left homotopy inverse. This result is achieved through the construction of an inclusion map EMB nu, dn2, dn, right-pointing arrow EMB nu, dn2, S1 times dn1, which itself is the inclusion portion of a homotopy retract. The left homotopy inverse arises from lifting and embedding dn2 right-pointing arrow S1 times dn1 to the universal cover, identified with a copy of dn with 2 points removed from the boundary. The scanning map EMB, dn1, S1 times dn1, right-pointing arrow omega EMB, dn2, S1 times dn1, and its properties are then examined. For n equals 2, Gramma's work, 17, demonstrates that the scanning map is a homotopy equivalence. When n equals 3, Hatcher's results, 18, show that both spaces are contractible, making the scanning map a homotopy equivalence. However, for n is greater than or equal to 4, less is known about these scanning maps. In the case of n equals 3, the mapping class group pi0 diff, S1 times D3, is proven to be not finitely generated in 4 and 5 via the map pi0 diff, S1 times D3, right-pointing arrow pi2 EMB, D1, S1 times D3. The intermediate map pi0 diff, S1 times D3, right-pointing arrow pi1 EMB, D2, S1 times D3, has a kernel isomorphic to pi0 diff, D4, resulting from the handle attachment homotopy equivalence, diff, S1 times dn1, asymptotically equal diff, dn, times EMB, dn1, S1 times dn1, described in 4. This reduces the study of the scanning map pi0 diff, S1 times D3, right-pointing arrow pi2 EMB, D1, S1 times D3, to the final step pi1 EMB, D2, S1 times D3, right-pointing arrow pi2 EMB, D1, S1 times D3, i.e., the loop space functor applied to the scanning map EMB, D2, S1 times D3, right-pointing arrow omega EMB, D1, S1 times D3. Finally, the deloopings of the spaces diff, dn, and EMB, dj, dn, are studied in 32 and 33. Investigating whether analogous retraction results exist for the deloopings of the scanning maps diff, dn, right-pointing arrow omega EMBFR, dj, dn, is proposed as an interesting and deserving area of future research. The authors discuss the limitations of applying Theorem 2.1 to construct a homotopy equivalence between the space of embeddings EMB, D2, S1 times D3, and the loop space of embeddings omega EMB nu, D1, S1 times D3 union H3. The boundary circle of the embeddings in EMB, D2, S1 times D3, is homologically trivial, failing to meet the required conditions. Instead, the authors highlight the significance of Frese-Scherchenwellwalker's work, which deloops the homotopy fiber of the map from embeddings to immersions, providing a concrete description of its rational homotopy type in terms of graph complexes when nj greater than 2. This could shed light on the codimension 1 scanning map EMB, dj, dn, right-pointing arrow omega EMB, dj1, dn, in rational homotopy, although the lack of understanding of the induced map EMB, dj, dn, right-pointing arrow IMM, dj, dn, in rational homotopy when j greater than the first of may be a limiting factor. The Freudenthal suspension map, EMB, d1, dn, right-pointing arrow omega EMB, d1, dn plus 1, is also discussed, defined via 2 canonical unknotting operations and known to be 0 on rational homotopy, but potentially homotopically non-trivial. The authors then explore the homotopy equivalence diff, I times n, asymptotically equal omega EMB, 1/2 times n, I times n, which can be extrapolated to a sequence of scanning maps distinct from those in section 2. These scanning maps involve Bott-style cancelling handles, disk bundles over manifolds rather than plain disks, typically occurring in functions with symmetry, such as the trace functional on the orthogonal group O, n. Finally, the authors present an analog to Theorem 2.1 in the Bott case, taking the form of a homotopy equivalence EMB, MDK, n, nu, MDK1, asymptotically equal omega EMB, MDK1, n. The paper explores the concepts of stabilisation, scanning, and handle cancellation in the context of embedding calculus and diffeomorphism groups, focusing on product manifolds. It introduces string links as a tool for examining homotopy types of these groups, particularly for product manifolds. The authors propose a new framework based on the Taylor Tower, constructed from spaces of generalized string links and maps to the Goodwillie-Weiss-Klein embedding calculus. This framework could simplify practical computations of homotopy and homology groups of embedding spaces. The paper also delves into the relationship between restriction maps and Cerf half-disk fibrations, noting that when j less than n, these fibrations are null homotopic via shrinking support argument. By modifying the standard diffeomorphism group and embedding space with their long versions and requiring the embeddings to have trivialized normal bundles, the authors obtain a fibration with a fiber homotopy equivalent to diff SNJ1 times dj plus 1. A cancelling handle homotopy equivalence is then established, connecting this to the standard diffeomorphism group in half-disk embedding space. String links play a crucial role in the paper in two key ways. First, as induced diffeomorphisms originating from low-dimensional homotopy groups of spaces of two-component string links, and second, as the form of the map used to detect diffeomorphisms of S1 times dn1. The lifts of an element of EMB, d1, S1 times dn1, to the universal cover result in an equivariant, infinite component string link in R times dn1. This indicates that string links could be an efficient tool for investigating embedding spaces and diffeomorphism groups. In the context of differential geometry and topological spaces, the Schoenflies monoid is a group structure on pi0 EMB, Sn-1, Sn, defined by the connectsum operation. This monoid is crucial for understanding the Schoenflies problem in dimension n equals 4, which states that the Schoenflies monoid is trivial. The Schoenflies monoid can be understood through a fibration sequence for EMBFR, dj plus 1, Sn-j-1 times dj plus 1, right pointing arrow EMBFR, hdj plus 1, dn. Right pointing arrow EMBFR, dj, dn. Where hdj plus 1 is a half-disk bundle over dj plus 1. The contractibility of this fibration sequence implies that the fibration diff, Sn-j-1 times dj plus 1, right pointing arrow EMBFR, dj, dn, is essentially the half-disk fibration EMBFR, hdj plus 1, dn, right-pointing arrow EMBFR, dj, dn, with the trivial diff, dn, factor in the total space and fiber. The connectsum operation defining the Schoenflies monoid involves relative surgery on both the ambient manifold and submanifold, requiring linearization operations relative to functions f and g about the embeddings dn-1 right-pointing arrow f, Sn-1, and dn-1 right-pointing arrow g, Sn-1, respectively, as well as an identification of Sn with Sn. The homotopy equivalence EMB, Sn-1, Sn, asymptotically equals Sun plus 1 times EMB, dn-1, dn, allows for the definition of the monoid structure on pi0 EMB, dn-1, dn, following from a linearization argument. The space EMB, dn-1, dn, consists of smooth embeddings Rn-1 right-pointing arrow Rn agreeing with the standard inclusion, 0, times Rn-1 subset of Rn outside of dn-1, and mapping dn-1 into dn. A binary operation on EMB, dn-1, dn, is defined by stacking embeddings, requiring rescaling and translation for precision. The Schoenflies problem in dimension n equals 4 is equivalent to proving that the Schoenflies monoid is trivial. This page provides a comprehensive overview of the Schoenflies monoid, its connection to the Schoenflies problem, and the necessary conditions for defining the monoid structure on pi0 EMB, dn-1, dn. The paper explores the monoid structure on pi0 EMB, Sn-1, Sn, and its connection to the connectsum operation. It is demonstrated that this monoid is a group for all n is greater than or equal to 2, and there exists an ontahomomorphism from pi1 emb nu dn-2 dn to pi0 emb dn-1 dn. This homomorphism is defined by lifting a loop of embeddings of dn-2 in dn to a path in emb h dn-1 dn, which then leads to a smoothly embedded dn-1 in dn that agrees with the standard inclusion on the boundary. The connectsum operation generalizes directly to all embedding spaces pi0 emb sj sn, where it becomes the classical connectsum operation on k-dimension 2 knots when n equals j plus 2 and the composition operation on pi0 diff sn when j equals n. The monoid pi0 emb sn-1 sn has inverses, as shown through a Curvaire-Milnor-style argument involving drilling a small open ball from Sn-1 and considering a tubular neighborhood of the manifold. The Schoenflies problem, a long-standing question in topology, concerns the triviality of the monoid of Schoenflies spheres, denoted as pi0 emb Sn-1 Sn. This problem has been resolved in dimensions other than 4, with recent work providing a novel approach to its resolution. A key contribution is the introduction of the group pi1 emb nu dn-2 dn, which maps onto the Schoenflies monoid, thereby offering a prescription for constructing all Schoenflies spheres. This development builds upon earlier research by Goodwillie, Klein, and Weiss, as well as Hatcher's proof of the Smale conjecture. The connection between the Schoenflies problem and the derivative map for diffeomorphisms of disks is also explored, revealing a deeper understanding of the underlying topological structures. Furthermore, the paper examines the rational homotopy of mapping spaces of operids, shedding light on the intricate relationships between these spaces. The introduction of the group pi1 emb nu dn-2 dn enables the construction of Schoenflies spheres through a well-defined process. This, in turn, has significant implications for the study of topological invariance and the classification of manifolds. The resolution of the Schoenflies problem in dimensions other than 4 represents a major breakthrough, with far-reaching consequences for the field of topology. Please provide the content that needs to be refined. The provided text seems incomplete, and I'm ready to assist you in transforming it into a concise, technically accurate summary suitable for voiceover narration.